Start the notes for today. I want to go over questions from the Alex assignment and the paper, the practice assignment. Pull it up over here. This one. So yesterday, you should have finished trying the examples on the back of Tuesday's notes if you hadn't already tried that Tuesday evening, and then checked those, okay? If you did not get a chance to try those and check those, you should still do that. And the video of me going over all of them is posted, as is the PDF of the completed notes with all of them complete. Okay, and then the next step in the learning path yesterday was the Alex practice. So I'm going to pull that up first, and we can go over any questions y'all had. Now, they won't be the exact questions that you had, but they will be similar type problems, and we can talk about the process and the strategies. Are there any specific ones that Sanal? Tell me what number it is, and I'll pull it up, and then you can, yeah. 7? Okay, so the problems that you got for this one, they say to find all solutions to the equation. Okay, so these are slightly different. In our notes, we were limiting the interval we were giving our answers on to either 0 to 2 pi or negative 2 pi to 2 pi. We were restricting it so because there's infinitely many answers for these questions, because we know that the sine and cosine waves it's cyclical, right? It just keeps hitting the same points over and over and over again, doesn't it? Okay, you can keep going around and hitting coterminal angle after coterminal angle. Okay, so in this case, if they are not giving us an interval restricting where they want the solutions from, they want actually all of them, we write that with the term. When we did this most recently was in our graphs of other trig functions, when we were graphing like sine, or not sine, but cosecant and secant and tangent and cotangent, and we graphed the asymptotes. And then for tangent and cotangents, we graphed the zeros. And you had some questions like, where are the asymptotes? At what interval are the asymptotes occurring? Or at what interval are the zeros occurring? Okay, this is similar to that. The way that Alex is notating it is with this k pi. We, in our notes, I believe we used n instead of k, but it means the same thing. It's just a variable. And they tell you right here, remember this means k is an element of all integers. Remember that double-backed z means all integers. Okay, so this is the format they're writing it in. Instead of writing in, pi in, they're using k pi, but that means the same thing. Okay, so for this particular one, we would need to isolate the cosine theta first, okay, by adding the root 3 to the other side and then dividing out the 2. Is everybody good with the process of isolating the trig function? Okay, so once you have that isolated, you have cosine of theta. I can't write on the screen in Alex like I normally do, so I'm just kind of talking you through it. Actually, I can just show the explanation and talk you through it that way so you can see a visual of what I'm saying. Okay, so you've isolated it, and it looks like this once it's isolated. Cosine of theta equals root 3 over 2. So once we get to this point where you've isolated the trig function, then you're answering the question of what is theta? What could I plug in here to make this true? Okay, and there's infinitely many answers, but we're just going to get the ones for one cycle, 0 to 2 pi. and then use those to write the expression showing that it repeats. Okay? So where around the unit circle is cosine's value root 3 over 2? And there's two places where cosine is positive, quadrant 1 and quadrant 4. So you can see here in quadrant 1, that's at pi 6, and in quadrant 2, that's 4, that's at 11 pi 6ths. Okay, so had it asked just for on the interval 0 to 2 pi, you would just list those two angles as your answers. But because it says all solutions, we have to add that plus 2 pi n, or in Alex's notation, that's 2k pi instead of 2 pi n. They're using k instead of n. But what that means, because if I hit pi 6, if I add 2 pi to this, doesn't it get me right back here to the same spot? It's coterminal. If I add another 2 pi, won't it get me here again? So I could keep adding any number of 2 pi's. Okay, so I could add 1 2 pi, or 2 2 pi's, or 3 2 pi's, or 4 2 pi's, etc. Or I could subtract. I could do negative 2 pi, negative 4 pi, negative 6 pi. Okay, and I go in the opposite direction. It would still get me back to the same place. So this notation is just our way of saying, instead of actually listing out all of these values, we just write it like this right here. So we say, okay, pi 6 plus 2k pi, where k is an element of all integers. So it's saying it's pi 6 plus any multiple of 2 pi. You'll keep getting to that same place. And then we do the same thing for the 11 pi 6th angle. If we kept adding 2 pi to it, we would keep hitting that same place, and cosine's value would be the same there. Does that make sense? Do y'all remember that notation when we were using it for listing like where the asymptotes would be or where the zeros would be? Okay, so it's kind of bringing it all back from what we've done before. Did you have another question, Snell? Okay. Do you want me to do, is there a specific one that you need me to look at, or just you? Okay. All right. Is there another one of the Alex problems y'all want me to look at? So on number 9, okay, this is another one that wants all the solutions to the equation in the interval. Okay, so this one restricts the interval for our answers, so we don't have to do that fun notation. Okay, it is already factored for us. This is in factored form, set equal to 0. So this one is ready to just do the split and solve, where we set each of those factors separately equal to 0 and solve each one. So it's like two separate problems. So for the factor on the left, 2 cosine x plus root 3 equal to 0. I would subtract the root 3 and divide out the 2. So that leaves me with cosine of x is negative root 3 over 2. The last problem I just went over, we just said that cosine was root 3 over 2 at pi 6ths and 11 pi 6ths. This one is the negative counterpart because it's negative root 3 over 2. So cosine is negative in quadrants 2 and 3. So our solutions for this are going to come from quadrants 2 and 3 at those pi 6th reference angles. So that should be 5 pi 6th and 7 pi 6th. Does that make sense? Now for the factor here on the right, cosecant of x plus 1/4 equals 0. I would subtract the 1/4. So I end up with cosecant x equals negative 1/4. Now, I don't know the cosecant values around the unit circle off the top of my head, but I know sine. and that's the reciprocal of cosecant, right? So if cosecant is negative 1/4, what would sine be? Negative 4. It's the reciprocal. So the question is, where is sine negative 4? Nowhere. Sine, that wave, that sinusoidal wave for sine and cosine, the range is -1 to 1. It doesn't go above 1 or below -1. So if that value, that range value, is outside that range, there's no solution for that factor. There is nowhere that sine is -4. If you wanted to visualize your cosecant graph, remember that's the one with like the U shape, asymptote, upside down U shape, asymptote, U shape. You remember that? It's like the wave flipped out. There was nothing in between those U shapes going up and down. That gap was empty between -1 and 1. So there is nowhere where cosecant is -1/4. Does that make sense? So the only solutions came from the factor on the left. Okay, and that for this particular problem, so we can list that out. So that would have been at 5π6 and 7π6. You can, oh, it doesn't show the work for it. So you can see this is what I was explaining. Separate the factors equal to 0 and isolate each individually. For cosine, we came up with 5 and 7π6. And for cosecant, it's never -1/4. If you didn't understand why that's never, you could have clicked on the Y, and it talks about sine being the reciprocal of -4, and sine, that's out of sine's range. We okay with that one? Were there any other Alex questions y'all wanted to look at or needed some help on? Okay. If you did not finish this, you have until Friday at midnight. Okay, so you have tonight and tomorrow night still to go back and finish this Alex. And I believe each question attempt I set at 3, and then the assignment attempt at 2. So if you missed some and you still need to go back and you want to try and go back and correct those, you can before midnight Friday night. Yes. 3. Okay, so this is kind of a spiral review. This is inverse sine. Okay, so the latter ones were solving trig equations, more like the recent notes we took on Tuesday. Okay, these beginning ones were spiral reviewing what we had learned at the beginning of the week and at the end of the week before Thanksgiving. So inverse sine, that's the inner function. We have to do the inside first, and then we'll worry about the cotangent. So this is a composition with inverse. So this is asking, where is sine -2/5? Now that's not a value that we have memorized from the unit circle, but it is in the range. It's between -1 and 1, right? It does exist. We just don't know exactly at what angle. So we would have to sketch a picture of the angle and use Pythagorean theorem to come up with the missing side of the triangle. So this is combining what we did back in, I guess it was unit 2, where say you had one trig ratio or an ordered pair and you drew a triangle in the correct quadrant and did Pythagorean theorem to find the missing side, and then you were able to give all the other ratios. Do y'all remember doing that? It's been a little while. Okay, so this combines inverse compositions with what we did back in unit 2. So inverse sine would be negative in what quadrant? quadrant 4, because we only have arc sine in quadrant 1 and quadrant 4. That's where we get our solutions. Okay, and so we're going to you would draw a triangle in quadrant 4. Okay, so with the radius coming out from the origin into quadrant 4 would be the terminal side of the angle. Okay, sine is y over r. So you would label the vertical side of the triangle 2 and the terminal side of the angle, the hypotenuse of the triangle, 5. Where does the negative come from? The y or the r? The y. The negative always is only going to come from the x or the y. R is never negative. Okay, so, and that makes sense because we're in quadrant 4. The y should be negative. So imagine a triangle. So like if this corner, if this is quadrant 4 and this is the origin, got this terminal side coming down here, and this vertical edge is -2, and this length here is 5. I would do Pythagorean theorem to find the horizontal leg, the x. Okay, so I would set up x squared plus -2 squared equals 5 squared. So the 2 squared is 4, the 5 squared is 25. I'd have to subtract the 4 over and get 21. And I have to take the square root of that. So I have square root of 21. Y'all, so far so good? So that's this horizontal length. Now that picture is my answer for this inside function. I just drew a picture of this angle in quadrant 4, this reference angle. I don't know what the measure is, but I have all of the sides to set up any of the ratios. So now I can say, okay, well, what's cotangent at that angle? Well, cotangent's ratio, that's the reciprocal of tangent. Tangent's y over x. So cotangent is x over y. So the x we said was root 21 and the y was -2. So it should be square root of 21 over 2, and the whole thing should be negative. So I'm going to put a negative in front. See if I did that right. Yeah. Let me click on explanation so you can kind of see a visual of that. So here's that picture I was trying to describe to you. You feel okay about that? That picture, this theta, that's the answer to the inside function. So then we just say, okay, what's cotangent there in this picture? Good. So a lot of this is combining things we've been doing in previous units and previous lessons. It's kind of bringing it all together. Any other Alex questions? Okay. What about the paper practice? This one here, practice solving trig equations. Now this one got edited. It started out initially just being linear form, and we mixed in some quadratic. So I imagine some of your questions that you have on here are about some of the quadratic form ones, like 7 and 8, perhaps, because we didn't have examples like those in the notes Tuesday. Besides 7 and 8, because we're actually going to talk about those in today's notes, and then you'll be able to go back and do these. Besides 7 and 8, were there questions on this that you want to go over? 2? All right, so on number 2, and I can write on this one, you isolate your trig function. So we add the 1 to the other side. So it becomes +1. And then we divide the 2 over. And then how do I get rid of that square? When I take the square root as an opposite operation to solve, I've got to put plus minus. Okay, so I've got sine of x is positive or negative. Now, when you take the square root of a fraction, you're taking the square root of both the numerator and the denominator, right? So the square root of 1 is just 1. The square root of 2 is not a perfect square. What would this become when I rationalize it? Yeah, once I rationalize, that root 2 moves to the top and I'm left with a 2 in the bottom. Now that should look familiar. What reference angle does that happen where sine is root 2 over 2? 45 or pi fourths if we're in radians. Okay. Now, it's positive or negative, so it's not limited to a certain quadrant. It's going to be all 4 quadrants, because in 2 quadrants, sine is positive, and in 2 quadrants, sine is negative. So if I were going to list all of those out, that would be pi fourths, 3 pi fourths, 5 pi fourths, and 7 pi fourths. Now, it says up here, all values. So that means it wants the same format as we did in that Alex problem where we say this is only the answers for 0 to 2 pi. It wants all values. So I would have to just list how often we're hitting this value. Now, this one's a little different because if it's at every pi fourth reference angle, I don't actually have to write each of these out plus 2 pi, because what's the skip from pi fourths to 3 pi fourths? What's that spread? How far do I go? And then from 3 pi fourths to 5 pi fourths, how far do I go? And then from 5 to 7 pi fourths. So I really only have to list pi fourths plus all of the multiples of that plus pi halves. So plus pi halves n, or k, or you can put the n in the numerator, or the k in the numerator. Okay, so as far as like the notation of that, there's a couple of options. Does that make sense? Okay, and then I have to notate that n is an element of all integers. So that is all the solutions. This list is just the solutions from 0 to 2 pi. Y'all understand the difference? What else? Oh, let me point out, because Will pointed it out or asked me about it. There's a typo on 10. It says arc, inverse of arc sine. They're not, both of those are not supposed to be there. It's supposed to be arc sine or inverse sine, not both. So just mark one of them out. That's just a typo. Any others? Or was it just 7 and 8, Victoria? Number 1? All right, so we've got cosine on both sides of the equation. So I want to isolate cosine, so I need to combine like terms. I need to get them to the same side and then move the numbers away from it, right? It's just like if this was an x equals 3x minus 2. I would get all the x's to one side, right? So I'm going to get all the cosines to one side. Doesn't matter which direction you go. I'm going to subtract the 3 cosine over here since the constant's already on the right side. Okay, so if I subtract 3 cosine x over, gets rid of it over here, 1 cosine x minus 3 cosine x is negative 2 cosine x. And then over here, I'm left with that negative 2. Then I can get rid of that negative 2 coefficient by dividing. That reduces to just a 1, right? So I'm just now to a point. I've isolated the trig function and I want to know, where is cosine 1? There's only one place from 0 to 2 pi where it's cosine is positive 1. That's at 0 or 2 pi. I mean, those are coterminal angles, so it's at 0. But they want all solutions. So it's going to be at starting at 0, every 2 pi after that, right? So this one is going to be the 2 pi in, or the 2 in pi. I don't care what order you put those numbers in, or the letters and numbers in. But we have to notate that n is an element of all integers. Did somebody else have their hand up a second ago? Yes. All right, 6 has more than one trig function. So we talked about in our notes Tuesday, if there's more than one type of trig function, we want to move it all to one side and set it equal to 0 to see if we can factor something out to separate into multiple factors. So I'm going to subtract the 3 sine x over to the left side. So I'll have the sine x tan squared x, oops, not equals, minus the 3 sine x, and then I'll be left with 0 on the right. So here I have two terms with a common factor. This is GCF factoring that I can do here, greatest common factor. What is the greatest common factor? Sine of x. They both have sine of x. So I'm going to divide out that sine of x and then put in parentheses what I'm left with. What am I left with in this term? If I divide out that sine x, just the tangent squared x. Minus, and what am I going to be left with here if I divide out the sine x? So now each factor only has one trig function, so I can split and solve. So I can set sine of x equal to 0 and tan squared x minus 3 equal to 0. The left one, it's already isolated the trig function, good to go. On the right side, I would have to add the 3 over to the other side. I'd have tan squared x equals positive 3. And then I would need to take the square root. And when I take the square root, I have to remember to do plus or minus. So I would have tangent of x is the positive or negative square root of 3. So now I've got the trig function isolated for both factors, and I'm ready to start answering. And this one, luckily, this is just between 0 and 2 pi. So I only have to do like one revolution. So where is sine 0? At what angles on the unit circle is sine's value 0? 0 and pi. Why am I not writing 2 pi? Yeah, this is a parenthesis here. We have a bracket on 0, so include the 0, not the 2 pi, because that's just repetitive, right? Okay. Now for tangent, where is tangent? Which reference angle is tangent root 3? At 60, or in radians, that's pi thirds. Okay. And am I limited to a certain quadrant? No, it's plus or minus. So it's all of them again. So I'm going to list all of the pi third reference angles. Okay. So that would be pi thirds in quadrant 1, 2 pi thirds in quadrant 2, 4 pi thirds in quadrant 3, and 5 pi thirds in quadrant 4. So all of the, if you want to list them out all in one line, you can, or you can just box them separately. That's fine too. But so there's 6 angles that you could plug into this equation and it would be true. The left would equal the right if I plugged any of those angles in for x. Yes. Anytime you take a square root as your like step to solve an equation, you always have to put plus or minus, because it could be, if you think about this, the the best way to describe. It might be best to show not with trig. Let me just get a number, like pick a number to show you. So like if I say x squared is 4, and I want to know what x values would make this true. And so I take the square root of both sides to get x by itself. The square root of 4 is 2, but -2 would also make this true because when I square the negative, it comes back out to +4. So when we do that, we always put plus or minus because when we plug it into check, either the positive or the negative being squared comes out the same. And so we can't limit that. We have to list all of the possible solutions. Any others besides 7 and 8? All right, now this, oh, that's like 7 and 8. Any besides 3, 7, and 8? Okay, this one immediately you don't notice that it's a trinomial, but if I move this 2 to the other side, that's the first step. You can go ahead and do that. It becomes +2 equals 0. Now it's a trinomial. You have a squared, a linear, a constant, right? Okay, so that's similar to the others, and that's what we're going to look at today in just a sec. So y'all ready to look at that? Okay, and then once we do these notes, you'll be able to go back and do 3, 7, and 8 if you had skipped those. All right. Oh, no, that's it. That's the last notes. That's not the new one. Unit 4, building block. Let me try. These both are the same thing, I think. They both say third of the period, though. One of them's supposed to be 6th. I saved it wrong. It's the completed one. Sorry, this got saved under the wrong name, I guess. I can't tell. Oh, that's the old one. What the heck? Okay. I thought I had saved it on the desktop for me to open quickly, but let me go back to my folder and find it for us. For 6th period. Okay, so those quadratic form, if it was a quadratic where we could do GCF, y'all seem okay with those. Y'all are good with GCF factoring, but you may need a refresher on your trinomial factoring technique. Okay, so I don't want to take, we spent a little more time on questions on the assignments from yesterday. So I don't want to take time to let y'all do these on your own. I'm just going to go ahead and power through them so we can get to the examples we need to. But if you were to try these, these get progressively harder. A and B are more like maybe like algebra 1 level factoring, and then these get more to algebra 2 level factoring. Okay, so this is just a review. This one is GCF. If I have both of these terms have something I can divide out, what is it? 3x. They both are divisible by 3 and they're both divisible by x. And that's what factoring is. It's literally dividing out what they have in common. And you put what you're dividing out outside the parentheses and then what's left inside. So here the 3's reduce and the x squared over x reduces to just an x. Plus, and then here the x's reduce and then the 12 over 3 is a 4. And that's factored. In B, we start off the same way with GCF. They both have what that they're divisible by? They're both divisible by 3. This one doesn't, bless you, this one doesn't have the x here this time. So it's just the 3 coming out, leaving me with the x squared minus 4. This one's not done yet. What do you have in parentheses here? Yeah, you have, it's the difference of 2 squares. Okay, when you have two perfect terms that are perfect squares and one's being subtracted from the other, difference of 2 squares is a type of factoring y'all learned. I abbreviate it DOTS, difference of 2 squares. The 3 out front is unaffected. It's still there. Get my red pen back. That 3's hanging out, just chilling out there. Okay, but the inside here, the difference of 2 squares, this binomial is we're able to factor into 2 separate binomials instead of having that squared. Do y'all remember what to do for difference of 2 squares? What do you do? Yeah, you take the square root of each of those terms, which would be x and 2. And those are the terms that go here, and you do one positive and one negative. So now that one's completely factored. So we were able to do GCF factoring, then difference of squares factoring. Now C is a trinomial with an understood A value of 1, right? So I don't need to do the like little X organizer, whatever you call it, that a lot of y'all do pretty often. If A is a 1, you don't need to bother with that's just taking up extra time. If A is 1, you just need to ask yourself what multiplies to C and adds to B. What multiplies to 7. So factors of 7 that would combine to negative 12. Are there any? The only factors of 7 are 1 and 7, and that will not add or subtract to 12. So this is not factorable. Okay, if that was switched around, and that was 7x here and 12 out here, we could do that, couldn't we? We could do 3 and 4, but it doesn't work that way here. This one's not factorable. Now here we've got a trinomial. This one is factorable, but the A is something other than 1. And so I think sometimes that stresses y'all out a little. But this is your trinomial, we're trying to break it down into 2 binomials, right? If this A value is still a prime number, I still don't think you need to do that whole Xbox thing. But you can if you want. I'm going to go over it in a minute. But I'm going to first show you, this is how I would factor this. What are the only factors of 3x squared? Yeah, 3 and 1. So 3x and 1x. Okay. So then I know factoring is like the reverse or opposite of foiling, isn't it? We know the outer values get multiplied and the inner values get multiplied and then added together to get this middle term, right? So instead of saying what multiplies to -8 and adds to -2, because now there's some other value here in play, I'm still looking for factors of -8, but they're not going to just on their own add to -2. The one that is placed here would get multiplied by 3 first, right? So 8 and 1. If I put an 8 here times this 24, no way I'm getting to 2. What if I flipped it and I put the 8 over here and the 1 here? That's a 3 and an 8, not combining to 2, is it? What are the next factors of 8? 4 and 2. If I put a 4 here, that would multiply to a 12 and a 2. That's not getting me there. But what if I switched it? What if I put the 4 here and the 2 here? That would be 6 and 4. That would subtract to 2, wouldn't it? Yes? So then I just need to check that I get my signs correct. It has to multiply to a -8. So one of them has to be positive, one of them has to be negative. But when I combine it all, I want -2. So the one that's going to multiply to 6, that needs to be the negative. And this, the positive. Okay, it doesn't always take that long. I was kind of talking you through the process. Okay, but that's just guess and check. Just think, okay, if I plug these factors in, will it work? It will or won't work. And I just check it in my head until I find the ones that work. Okay, now, if you prefer, you can do your little X thing. Okay, so you're putting in the top the A times C, right? A times C goes up here. So 3 times -8 is -24. Okay, and then your B value goes down here, which is -2. So we're asking ourselves what multiplies to -24 but adds to -2. What do y'all get? All right. Now, I think most of you do from here, some of you take it to box method, some of you replace the -2x with -6x plus 4x and have 4 terms and set up grouping, right? And then do your GCF of each group and you come up with your factors that way? Yes, no, maybe so? Okay. There's a shortcut, which I don't know if many of you, it doesn't seem like people have seen it before. Take these terms that you came up with, -6 and 4, and above them, we're going to put this value that we're dividing out. So the 3x in this case. And now take a look. 3 over -6, does that reduce? What does that reduce to? X over -2? 3x over 4, that doesn't reduce, does it? Now look at the factors. X minus 2. 3x, and that's a +4. 3x plus 4. Y'all see that shortcut? Okay. We will finish these up tomorrow. Y'all can go back and try and do more of the practice in Alex and the other one if you hadn't finished, but you'll have time after we finish these notes up tomorrow to do that as well. Let me stop this recording real fast.